In the last lecture, we took the time, and it required some time, to derive this expression for the input admittance of this, for this system right here, this projector. It's a ring projector, polarized this way, electroded that way. And it took some effort, but it's good because we're finally now able to rigorously derive what's going on for piezoceramic materials or piezoelectric materials. So here's what we got. Here's the input electrical admittance. This is due to the mechanical motion, and you can see because it's got the mechanical impedance here, and this is the electrical. So the way we look at this is, if there's no mechanical motion, we can do that by setting this equal to infinity, right? Infinite mechanical impedance. We call that blocked, right? If the system is blocked, what we see is this, and it's acting like admittance I omega times a constant. It's acting like a capacitor, which we knew, of course, but that was qualitative. This is quantitative. We now have an expression for the blocked electrical admittance. Or, well, we now have the way we look at this is, from a more basic point of view, we now have an expression for the blocked capacitance, okay, when there's no mechanical motion. That's this C0 right here. There's an electrical effect due to the mechanical motion because this is a transducer, and this is the motional admittance right here. And we found, and here's the expression for it. And we're going to write this as n squared over Zm, where n is equal to this. And Brian is good about this in the equivalent circuit here, which we're going to discuss. These expressions are listed right here. And right now we have no mechanical resistance, but you can add it in. It's easy to add in, okay? And one of the reasons that can be important is you can have a load here. And often loads are typically modeled by just a pure resistance. Okay, so you can see that we have the input admittance is the sum of these two admittances. So those, thinking of these as elements, as circuit elements, they're going to be in parallel, right? Because admittances in parallel add. It's the opposite of impedance. So to get an equivalent circuit for this is what it looks like. Now, this is confusing because why is the transformer there, right? So I finally realized, I think, just last night, why Brian has, we'd like to get rid of the transformer, and we can easily do that. But I can now finally appreciate, I think, why he did this. He wanted to be able to state the mechanical quantities here. See, this is not inductance. This is mass. Okay, it's analogous to, of course, an inductor, but I think he wanted to be consistent here. So he threw a transformer in, and you know, transducer people throw transformers around all over the place because a transducer is a transformer, right, as we've discussed. So, this turns out to be the equivalent circuit, and if you work with it, you'll see it's equivalent to this. The best thing to do, I think, at this point is to remove the transformer, okay, to get to the circuit that we're all familiar with, that we've been using without having rigorously proved it, okay? So how do we do that? Well, let me remind you, it's way back in chapter 2. When you remove a transformer like this, you want to take this out, it modifies these parameters. It actually has to, because right now these are mechanical. When you remove the transformer, you will have a fully electrical circuit. These will be in electrical units. Okay, this will be electrical resistance, not mechanical resistance. They have different units. So the rule is, and you might remember it, but you can go back and look at it, is the resistance and the inductance simply get divided by n squared. N is the ratio of turns, right, which is a dimensional quantity here. This is an abstract transformer, right? So That N quantity appears here in the conversion. You divide the mechanical resistance by N squared, and that will give you units of ohms. You take the mass and divide by N squared, and you got to multiply the compliance by N squared, and that will give you the mechanical, electrical equivalent capacitance. So when you do that, okay, and come up with this now fully electrical circuit, you can see, and I'll let you do this if you're interested, but you can do it in your head, I think. You'll see that it's equivalent to what we just got here. So this is the equivalent electric circuit, the one we've been using, and it's very plausible. We know we have a capacitor, and we know that there's mechanical motion. So it's very plausible to, forget the transformer here, to do, and these are now in electrical units, to write this down. And that's why we did it, in order to make progress. But now, finally, after laying all this groundwork for weeks, we derived it. We can derive it. And we're going to derive, I thought this was the only one we were going to do, but I mentioned that maybe a lecture or two ago, but I was wrong. We're going to do this whole chapter, a lot of it is going to be involved in deriving from fundamental principles, the equivalent electric circuits. Okay, now there's more. There's some interesting physics with this particular projector or vibrator. And as almost always, we look at, in acoustics, we look at resonance. Resonance almost always plays a very important role. There is a resonance here. If you start at a low frequency, this is quasi-statically moving out, in and out like this. As you increase the frequency, eventually you're going to hit a resonance. And it's physically obvious. This is going, you can see there's going to be a resonance here. It's going to be similar to a mass on a spring. And quantitatively, we can get at it by look at the minimize the impedance, and it's going to be the mechanical impedance. And you can see it's going to lead to the usual resonant frequency, usual mass on a spring resonant frequency. And let me remind you, this is the compliance. The stiffness is 1 over this. So this is the square root of k over m. It's just like a mass on a spring. Now to deal with it here, we want to put it in a transparent form. If you substitute our expressions for the compliance and the mass, which we established previously, you get this. And now, the best way to write this is to recognize here that, to recognize the appropriate wave speed here. Because we're assuming a wavelength that's large compared to the transverse dimensions, right? And because the transverse dimensions are small compared to the diameter, you can imagine spreading this thing out into a bar. The appropriate modulus here is going to be Young's modulus. We have compressions and expansions, and the bar, if we think of it as straightening it out, is allowed to expand and contract in both directions. So that's going to be Young's modulus. So the relevant speed here, remember, it's always the square root of the stiffness divided by the inertia. And in this case, the stiffness is Young's modulus, and the inertia is the density. So what this is, and in this case, the Young's modulus is just 1 over this entry in the compliance matrix here. So we can write this expression for the resonant frequency very simply in terms of the speed. It's just the speed divided by the radius. Okay, that's what it's. Now this is not, I don't think this is an obvious expression right here. Okay? And I'll talk a little bit more about that in a minute. But this is what it is. Okay, and it's just simply comes from this. We know this has to be true, and this is just substituting and recognizing the appropriate wave speed here. Now, let me remind you again from what I tried to emphasize it yesterday. Our theory here is only for radial, it's assuming purely radial motion. If you look at any mass, any element of mass, it's moving directly out and directly in. There's no motion like this. But that's not the only kind of motion that this ring can have, right? Here's the, this is a representation of the highly exaggerated representation of the radial mode. So think of the dashed line as the ambient case or equilibrium, and that being the average, it's the average circumference there. This ring is moving purely radially outward and inward. So it moves out and it will contract transversely. It moves in, it'll expand, right? And it contracts when it moves in, so it gets thicker. That's what I'm trying to represent here. Okay, greatly exaggerated, right? For typical solids. Maybe you could see this with Jello, I don't know, but then you got to deal with Jello, which that's probably really hard to deal with. Does anybody know what Jello is anymore? It was popular when I was a kid. I have no idea why. I think it's because it was colorful. So you guys know what Jello is? For instance, don't know. Yeah, they don't have a clue, see? So it's not universal, is it? Okay. Well, anyway, enough of Jello. So if you did, you could see something like this in an exaggerated sense. But there are clearly angular, or what we usually call azimuthal variations. So here's a representation of that. This is the, instantly. So what's the next radial mode? Anybody? It's a trick question, kind of. But that's it. There's just one radial mode. You can't have any more. Yeah, we tend to think we're all adulterated by acoustics, where we think, we see the water cooler, as we discussed last quarter, or we see a acoustic resonator, and we think of all these higher order modes like you did in the lab last quarter. No, there's just one mode here. There's just one radial mode. That's it. On the other hand, for the azimuthal modes, there's going to be a sequence out to infinity. Here's the fundamental azimuthal mode. And the idea is that it's going, I'll do this, it's just the ring's going like this, right? I don't know why this doesn't look right. These aren't. I wouldn't say those are nodes. There's displacement there. Oh gosh, how did that ever happen? Okay, I will look into this. So ignore this for now, okay? But the idea is clear, right? It's going to be able to go like this. When it's moving this one, there's displacement this way. This is going to bulge, and this is going to contract, right? And then half a cycle later, it's going to look like that. And how many wavelengths do we have around here? There's an integral number of wavelengths. Do you see it's one wavelength? It starts, look at the, you can look at the compression here. And as you go around, yeah, I can see why I called these nodes, but I think I need to clarify this. So here there's no compression or expansion. There's an expansion here. We go down to none here, then there's a contraction here. Go back to here, and we get back to here. We've gone around one cycle, right? That's one wavelength. So even though our theory doesn't apply to this case, we know what the resonant modes are going to be, right? Because we can imagine taking this and just spreading it out into a bar. And we've got one wavelength on this bar. So we know what we can write down easily what the resonant frequency is going to be. And the wavelength here is large compared to the transverse dimensions. As long as the wavelength is large compared to the transverse dimensions, the Young's modulus will be the appropriate modulus, as we've discussed before, right? Now, if you go to very high modes, we have a really tiny wavelength here. It won't be the Young's modulus anymore. It'll be the modulus of unilateral modulus. I wish they could come up with some kind of short name for this. The modulus of unilateral extension and compression, right? Okay, but that's much higher. Let's just think of wavelengths here that are going to tend to be long, that are roughly large compared to the transverse dimension. So it's going to be Young's modulus. So what's the frequency? Well, now watch this carefully. Look for sleight of hand here. This is really amazing. So that we're going to call that, we're going to use a 1 subscript for that mode. We use 0 for the radial mode. So and the next one will be twice this frequency. They'll be harmonic. So omega is equal to ck, right? Where c is, of course, that's on the previous slide. That's the speed of sound due to Young's modulus. K is 2 pi over the wavelength. The wavelength is the circumference, the ambient circumference, right? The 2 pi's cancel, and we get this. And this is really amazing. I think this is amazing. It's identical to this. So what we've found here, and it's really undeniable, is that the frequency, the frequency of this pure radial mode is equal to the same frequency as the first azimuthal mode. It's the same frequency. So you think, well, there must be a connection. Well, I can't find it. I tried, I can't find it. And I went and asked a professor here who was good at this kind of stuff. And he hadn't taught this for a long time. And he immediately told me the answer. Okay, so this is Professor Baker. So he had evidently thought about this and had left a permanent mark on him in his brain, okay? I'll never forget this. I kept saying, is this a coincidence? I said, what's going on here? He says, it's a coincidence. He thinks it's a coincidence. So if you can, and you know, I don't know if I searched any literature or anything on this, but if you can come up with a connection, why these two things are the same, we would love to know about it. It appears to be just a coincidence. Now, it's important from a practical point of view, because suppose you actually had a ring here, and that's, again, the bottom line of this course, you know, is real transducers, and you're driving it, and you start to get near this resonance. What's going to happen in a real system? Remember, you're driving it electrically, right? So you might think, you know, theoretically, I'm driving it electrically, it's just going to resonate. And then I can go above resonance, and then the amplitude is going to go down. That's not what happens in real systems. You're going to excite this mode. Because it's not perfectly symmetric. There's slight asymmetries. And all it takes is a little bit, and you're going to, energy will couple under there. I've seen this many times over decades, okay? You know, we would like to think everything to be nice and simple, but reality is often different. And so this happens a lot in acoustics, where slight asymmetries. You shouldn't excite something. The symmetry dictates, you know, we have a nice symmetrical situation here. We're driving like this, we see this. Why should we couple into this? Well, slight asymmetries will do it. Reality does it, okay? So you need to be aware of this in a practical sense. This is going to limit you, because once you start to excite these modes, our theory breaks down. Remember, all of this stuff, all this complicated stuff here is for only purely radial motion. This equivalent circuit, this is only for purely radial motion. All right. Okay, any questions? So that's good. It only took us, I don't know how many weeks to be able actually to derive something from scratch, you know? You'd think you would do this early in the course. We couldn't. There's too much groundwork to lay. Now, we assumed if you look back, we have no load on this. To sonar people, what that means is you're operating in air. I keep telling you this, and I'm going to keep telling you it, because it's an incredibly useful thing. You have to test transducers. You can't trust manufacturers' specifications. You have to scope them out. You got to check them. And one way to learn to get the parameter, in other words, get those parameters that you need to go into to calculate the sensitivity, for example, right? So when you do that, it's very important to be able to test it with no load, and that's done in air. Now, technically, there is a load there. The air is loading it. You're going to be sending out sound. But compared to water, air is like a vacuum, right? So I've said this many times, and I'm going to keep saying it, and you're going to finally do it, I think, this week in the lab. You'll do this. So I think this week, this lab meets downstairs in the tank room. You guys know the tank room? You're familiar with the 025? Okay, or 2.5 now. They took the 0 off to save money when they renovated the building. I don't know. I don't care anymore. Okay, so anyway, right. So now we did this whole theory for no load, which is useful because air is approximately no load. But what about the actual application where you want to have it when you want to have it a load in water? Well, you could go through the whole theory again, but the answer turns out to be very plausible if you think in terms of impedance. So this is yet one more example of why particularly transducer people can't live without impedance. So here's the idea. We have a force now. Instead of 0, what we meant no load is no force on the, and we're going to take it to be on the outer rim. We're going to assume that it's restricted to that outer edge, okay? There'll be a load force now, and we'll assume it's a uniform pressure, which is the typical case. I haven't emphasized that in this class, but we'll start to see it more and more. The typical case here is an element. You may have a sonar projector that's composed of a lot of elements, but if you look at each element, the wavelength is almost always large compared to the element. That's really convenient theoretically, because what that means is it's going to be the same, like in this case, the pressure will be the same here. Well, if thinking of this as a driver, I guess by symmetry the pressure has to be the same. But okay, but in this case, if you think of it as a hydrophone, right, a sound wave coming in, this is a hydrophone element, all the surfaces will be subjected to the same pressure because the wavelength is large. That greatly simplifies calculus. We'll make that assumption a lot in this course as we go on, okay? So anyway, this is standard. We have this constant pressure. The force is going to be the pressure times the area. Don't worry about the minus sign. It's not really important. So there is a specific load impedance. Okay, this is like a local load impedance. It's the pressure divided by the velocity, not the force. The force is integrated over the whole ring. We'll get there, but first of all, you want to recognize that we're going to have some specific load impedance here, which is going to be the pressure, and let's get whatever that may be, divided by the velocity. Okay, this is a radial velocity. Now, if you go back to our equation of motion, you can add this in the Newton's second law. You can add this in, right? But at this point in this sequence, you should have a strong suspicion of what's going to happen here. It's going to appear, you can show that it appears in the mechanical impedance as a resistance. Because this is a resistance, right? You're radiating sound. It's energy that's going away. It's not coming back. So you have this is a purely resistive load. And, okay, that's the case if, let's just assume it's a purely resistive load and we'll talk about it later, right? You know from last quarter that if the wavelength is large, is it purely resistive? No, you get a reactive part, right? Remember energy going to the near field? Okay, that's a problem in transducers, and I'll tell you how we get around it later on in the course, okay? And the spoiler alert is you're going to be disappointed. But it's because the situation can become extremely complicated. But we'll address that later. Don't worry about it right now, okay? So anyway, going back to here, it's not surprising that what you find here is this specific impedance becomes a global, or the impedance with the force. And not surprisingly, it's the specific impedance, the pressure per velocity, multiplied by this is the area of the radiating surface, okay, to give you the force. So this is, because this is force divided by velocity. So it's not surprising that this comes about. So all you have to do in our final expressions is just throw this in, right? So a huge advantage to going back and redoing the whole problem. So again, it's one of these examples of why, one of the reasons that impedance is so useful. Okay, any questions? Okay, so next in line of problems that we're going to solve here is something that's going to start off looking very much like the ring. Hopefully you'll see this now as looking like the ring, right? Because the ring is thin, we can imagine, you know, moving it, breaking it, and turning it into a bar like that. So this is similar, and this is going to be long. The length here is long compared to the transverse dimensions. So Young's modulus, from an elasticity point of view, Young's modulus is what's operating here. So we're starting off with that, but what we're going to do different here is this thing that I've talked about before, that we eventually have to confront, and this is our first confrontation. We're not going to assume low frequencies. Low frequencies, the bar will uniformly expand and contract. But as you start to increase the frequency, eventually you're going to see standing waves in there. So with standing waves, you can have nodes and antinodes, it's not uniform. So we're going to deal with that now. This is our first case of dealing with it. Okay, so let me look at this. Okay, so just try to keep this in your head. As always, I think, this is the polarized direction and the electroded direction, right? That'll be the Z direction. And then typically what we do, and this is what we did with the ring, we called X, you know, locally we called X this way. So X was kind of going around like that. So this is the same idea here. X is the long dimension. We'll assume the electric field E3 is uniform throughout. And we now know that's a good approximation, right? Because the dielectric constant, the relative dielectric constant, sometimes called kappa, is typically very large here. And you should be seeing that in the experiment that you got, right? Where you actually determined this by taking measurements. So you should be getting roughly in the order of 1,000. Is that right? Yeah, if you don't, then there's probably a mistake. Okay? Because of this, the field, as I discussed yesterday, the field lines get trapped. And so it's a good approximation. The uniform field is actually a good approximation. And because this is a piezoceramic with an axis of symmetry, E1 and E2 have to be 0. We don't need to worry about those. So anyway, what happens is the relevant, I need to add that, piezoelectric strain relationships here reduced to this. This is the stress, this is the strain in the X direction in terms of the stress and the electric field in the Z direction. And this is the displacement. And the bar is stress-free in the transverse dimensions, okay? So we're going to have this oscillating electric field where omega is not sufficiently small anymore, such that we have uniform expansion and compression. We're going to have standing waves. So we can write down what the solution has to look like here. When you have a standing wave, you know that it's going to be spatially a sinusoid, and then it's just going to oscillate in time, right? So here's a general sinusoid. We have to put, we don't know the phase. You can think of it like this, but then you'd have to add a phase there. So it's easier for us to equivalently not put a phase there, but just add the quadrature term. Right, it's mathematically equivalent. So that's the general form. And oh, by the way, omega and k are not independent, right? They're connected by the dispersion relationship. We talked about, it's the first time I've probably said it this quarter. No, I think I've said it. Yeah, so this is the relationship between the frequency and the wave number, or the wavelength. It's called the dispersion relationship. It's just a constant here. And it's going to be that speed that we've been talking about today, the speed of waves dictated by Young's modulus. Now, these are in general complex quantities, right? So what we need to do to proceed here, we need to get rid of this A and B in terms of other, more fundamental quantities. So how do we do that? Well, the answer is boundary conditions. That'll also incidentally discretize the omega and the k for the standing wave, the resonances. But we don't need to worry about that right now. So how do we proceed here? Well, the ends of the bar, okay, at x equals 0 and x equals the script L, are not loaded here. We're doing the unloaded case. We'll talk about the loaded case. We'll just get into it, I think, today, and we'll do it to complete it tomorrow. So we have this bar. It's going like it's, the ends are moving, but they're not subjected to any stress. So what does that mean? If I look at the end here, there's no load. There's no stress out here. That means that the bar there's no stress due to the bar on this. If you focus your attention on the face here, it has no mass. There can be no net force on this boundary, on this area right here. It has no mass. There's nothing out here. It's a vacuum or air. So we can't have any, there can't be any stress. Now, in usual elasticity, you would say, oh, then there's no strain. Okay, when we're not worried about any electrical interactions here. If I got this end here that's free, the bar can have no strain there. If it had strain, it would be exerting a force on this massless plane right here. But we have to be more careful here because this is piezoelectric and there's an interplay between the electrical and the mechanical. We look here and we see that at the ends we can have no stress. Okay, this is going to be zero, but there is a strain because of the electric field here. So this is different from the usual theory of elasticity. We have to be careful here. We write it like this. The boundary condition on the strain is that it's got to be D31 times E3. Okay, and E3 is going to be this, I've written here, this oscillatory form. So this is what we need to impose on our general solution. Here's the strain throughout the bar. It's just the rate of change in displacement with respect to x. We differentiate it, we get this. And now we impose the boundary conditions here at x equals 0 and x equals L. The x equals 0 is simple. You know, this drops out. We just get this. The x equals L gives us this. And now these are two linear equations in the unknowns A and B. They're easily solved. This is already essentially solved for. So you solve this for A, which is trivial, plug it into here, and then you can solve this for B, right? So here's what you get. These are the two amplitudes. So good, we've eliminated them. Now we take those, this really, I'll never forget this. So how did this half angle get in here? Where did that come from? God, I have to tell you, this really threw me when I first went through this. So I struggled with this, and I finally realized it's a very unusual trigonometric identity. You know, it's a half-angle formula, but it's probably not one that you've ever seen before. You've seen these, okay? These are well known. We've used them in this sequence, right? This is just a very unusual half-angle formula that's useful here. You can see this is all getting quite complicated. So when something gets complicated like that, people try to mathematically beat it down as simple as possible, and it's useful to use this unusual half-angle formula. So anyway, I remember I had to derive this because I think I'd seen it a long time ago, but so anyway, I wrote this in. You can derive it from the standard half angles. You can derive this, okay? So that's, almost went right by this, but this really, without this, it would be a lot messier. So as I said, people pay attention to those things when something gets to be complicated. Now, here's what we do. Let me just sketch this out for you here. We now know A and B. We can substitute these expressions into here, right? And then we can then we know S1 in terms of the electric field. We can substitute that in here, okay? And then we can find the stress in terms of the drive, you know, the electric field. And then we can plug that into here, and we can get the displacement field. Why is the displacement field important? I'm just trying to make sure you're not missing the basic stuff here. Look at this. Yeah, it's intimately connected with this current here. It's a fundamental variable in our system. We went through this recently, and we're going through it here, but it's going to be more complicated here. So here's what you get for the stress in the bar. You substitute that into the second piezoelectric strain, as I just mentioned. This is what you get for the displacement field. Okay, it's not simple. But it would look a lot more complicated if we didn't use this half-angle formula, okay? So now for some physics. Before that, we don't need to write this anymore. We don't need to carry this along. Why? Because it's the square of the coupling coefficient. We've seen this a number of times, and we're just going to keep seeing it in this course. So we replace this with that. That's nice. So now what we have to do is, before we proceed on, we need to interpret this here. Don't forget what we've got here. Got this capacitor. Okay, this is an equal potential. These are the bottom and top surfaces are equal potential surfaces, and it's the voltage, the potential difference between there has to be the same. You have to have the same electric field. This E3 has to be this. It's uniform to a pretty good approximation because of this, right? But it has to be. It can't vary as a function of x. E3 has to be constant because the integral of E3 over the distance, or just multiplying by the distance, is going to give you the voltage here. And the voltage, voltages have to be the same between those two surfaces, right? So that all seems very obvious. And then look at this. Our displacement field depends upon x. How can that be? You know, the electric field and the displacement field are connected. So what's going on here? Well, here's what's going on. We have compressions and expansions of this bar, right? Maybe it's better for me to just look here. So there is bound charge here. When this thing's polarized, it acts like it's a dielectric. It's like a permanent magnet, but it's electrical. So there'll be this. And again, you know what it's, do I need to do this again? Okay, it's like this, right? That's what's going on in here. So what happens when this, what if this point here is a point where it's compressed? What's going to happen to the charge density? It goes up. Now, however, remember, these are metal, this is metal here. These have to be, these are at some potential difference here. When this gets more crowded here, like this, okay? When you get something like this, the potential difference from here to here over here has to be the same as the potential difference here. So there's only one way out of this. It looks like this is, you're going to get a stronger electric field here. The voltage will be different here than it's there. It can't be. So there's only one way out. What is it? Remember, we also have free charge on top here. What's the free charge going to do? Well, it's going to bring this down. The electric field has to be, E3 has to be uniform because of the potential difference. It has to be the same everywhere. So what it's going to do, this is going to tend to increase the electric field, but the free charge is going to reduce this to keep the electric field uniform along here. So whereas the electric field has to be uniform here, the displacement field, which is dictated by the free charge, is going to be non-uniform because the free charge has to be non-uniform. It has to compensate for this. It's interesting. Okay, so that's why it's there. It's there as I remember an old professor said this once. This is there because it has to be there. Okay, I don't know if that makes much sense to you, but it's got to be there. You can see why he would say something like that. There's a physical meaning behind why it has to be there. And it's going to cause us a little bit of trouble, but we'll just kind of sidestep this because what we have to do next is we have to get that current. We've got to get an expression for the current. You know, ultimately what we're after here is like the admittance, right? And this is going to involve the current. So here's what we have to do. The current is, of course, the free current. All this charge here is permanent, but it's just its density is changing due to the elasticity, right? So we have to get at this current here, and that's the free current. And that comes from the D field. And we use, like I mentioned yesterday, this is fundamental law, Maxwell equation here for the displacement field. You integrate this over a volume, and the integral of a divergence becomes a surface volume, as you all know from, right, the standard vector differential calculus or whatever. So the surface integral will be the free charge. Why is this is important? Because the rate of change, I omega times the total free charge, is the current. We need to get the current. So what we have to do is integrate this over the surface. And now you actually have to do an integral because D is not uniform. Okay, so it can be done. I was trying to think if I confirmed this. I got a feeling I didn't, to be honest with you. Some of these things I confirm, right? That I feel I have to. Like, so when I first went through this, I had to confirm that. I couldn't let that go. And I think my suspicion is that for this integral here, we've got to integrate this. And then there's some I omegas. Just discuss it here. I may not have done this. I can't remember. Okay, but you can always do it, right? If it's above your threshold, if you don't feel comfortable with this, I would bet money that it's right. Okay, and I might have checked it. I don't know. But this is the result of what you get. So now finally we have the current in terms of the drive. Here's the amplitude of the electric field and all these constants that characterize our piezoelectric transducer. Now you'll notice how we write this. We think of the frequency as an independent variable, right? Now K, of course, is tied to omega. It's not independent. Omega is equal to CK, right? Okay. Okay. So the voltage because the electric field has to be constant, and it's going to be easier, we just multiply, to get the voltage, we just multiply by the thickness, as we've done many times before. There's no problem there. And now, again, the admittance is better than the impedance because I is complicated, V is not. So it's nice to have I in the numerator. So that's the reason here why it's nice to deal with the admittance. It's kind of strange, but that's the way it is. So here's what we get, the electrical admittance for our system. And this is what this would be useful for you if you want to probe out this transducer in air. Remember, there's no load, right? Because it's easy to electrically probe these systems. Okay, now what do we do with this? There is an equivalent circuit. We're going to do that next week in a problem set. Let's not worry about it right now. The next thing we should do is to check this, because we know that our bar is equivalent to this ring. So, for most purposes. So, our theory here should, in the low frequency limit, so K, or the long wavelength limit, our theory should reduce to the ring theory. So you can check, I'll just tell you that it does correctly reduce. You need to use the fact that the tangent of x, for whatever x is, this is just any variable, the tangent of x over x goes to 1 as x goes to 0. That's easy to prove. When you take this limit, this quasi-static or low frequency limit, here's what we get for the input admittance. And what this is here is, as you know from the lab, right, this is the free capacitance because there's no load and it's mechanically moving. It involves the blocked capacitance and the motional capacitance. We call that the free capacitance. It's simply the sum of the two. And as you know from the lab, the reason this is important is from here, the free capacitance is given by this expression. So by measuring the free capacitance, we can get at epsilon 3.3 for constant stress. That's important. So anyway, it can be shown that it does correctly reduce. And I've emphasized this. I don't think I need to emphasize this. I just said it essentially. Right. So that's why this is important. Now, there's stuff going on here. We have to investigate the standing waves here. And there's this somewhat of a surprise here. Resonance corresponds to the minimum value of the impedance, and therefore the maximum value of the admittance. right? And if you look at our expression, we have no damping here, so it's going to be infinite. If you look at that expression for the admittance, input admittance, you'll find that it's infinity. It's easy to see that it's infinity when KL divided by 2 is equal to the sequence, any element, any member of the sequence here, okay? And that corresponds to wavelengths. The wavelength being the fundamental, the wavelength is twice the length of the rod, and then it's 2/3. It's hard to see what this is, but the way it's better to say it in words. It's an odd number of half wavelengths. Okay, so if you look, if you think of the displacement here, I don't know, do we call it C? Is that the displacement? Displacement as a function of x here. And here's the length of our rod, right? So, and I'm going to plot the displacement this way, even though it's longitudinal. The fundamental is going to look like this. When this is positive, this is negative, so it looks like that. Then half a cycle later, it's doing that. So we can see here that in this case, we're getting half a wavelength here. All right? What about the wavelength? What about one wavelength? What about, we would normally think of that as a mode. So I can represent it like this. So now we've got, you can see that's one wavelength. That doesn't show up as a resonance here. So why is that? I remember this threw me for a while. And you remember intense things. When intense things happen to you, you remember them. There's a lot of intense things in this course that I remember from years ago. So how do you explain that? What's the bar doing here? Well, it's going like, here it's going like this. So if we think of this as going, let's say this way, this is going that way. So it's going like this. You can't excite that with our drive. It doesn't have the right symmetry. And the best way to see it is to think of a string. So the string is our friend, right? You did in 3119. If I have this, we have our electric field, we have this uniform drive. Think of, we're forcing this string uniformly like this. Can we excite this mode? Yeah, no problem. Can we excite this mode? No, they're out of phase. So your drive is like this. It's got the wrong symmetry. You could be putting energy into this half, but you'll be taking it out of this half. You can't excite that mode. Or any mode with an even number of wavelengths. So half of the resonances don't occur here. They potentially could occur, but due to the nature of our drive, this uniform drive, they're not there. And it's all in the math. The math tells you that, and you have to interpret it. Okay, so one more thing here. This is kind of interesting. This again, we'll get back to 3119. The lowest frequent resonance here is just going to be, the frequency is the speed divided by the wavelength. That's equivalent to omega is equal to ck. But experimentally, we want to deal with, frequency and wavelengths rather than angular frequency and wave number. So this will be the fundamental. The R stands for resonance. Okay, anti-resonance is not infinite admittance, it's zero admittance. And there, if you look at our expression, you get this nasty thing here. Okay? So, can you find, you know how to do this from 3119. How would you find, given some values here, how would you find the anti-resonances? Yeah, you get your calculator out and you would iterate, right? You can actually do it. It's actually fun, and it pretty quickly converges. Well, I think it's fun. and you make a little table and you zoom in, okay, and get it to any accuracy you want, okay? And the reason you have to do that is, what kind of an equation is this? There's a word for this. It's a transcendental equation. It involves a trigonometric function and just an algebraic function. You can't, mathematicians have somehow shown that you cannot analytically solve this equation. It's impossible. We might have discussed this last quarter. I can't remember if I think we, okay. So you got to do it numerically. That's trouble. However, we've strayed from the whole point here. The point is we don't need to theoretically determine these. We're going to be we can experimentally measure these two frequencies. So from the point of view from an experimental point of view, we take this relationship. You can express KL here. Here it is. There's a sequence going along. Here's it into frequency, and it involves the anti-resonant frequency. But you can lump all this other stuff together and put it as a ratio of the anti-resonant frequency to the resonant frequency, which is really not, may seem surprising to you, but this has to be dimensionless. So it's really not that surprising. So we can express KL here in terms of this, and these are measured quantities. So now, what can we do with this? What's the whole point? We can measure this. What can we get? We can experimentally determine K31, right? You get the point? It's like epsilon before. There it is. Okay, well, I think we better stop. We have to stop here. So tomorrow we'll discuss a load on the ends here.